Okay, integration errors. Number 4. Yes, I was very proud of this little problem after I wrote it. And I'm sure you guys don't have the same about it. Let me annotate a little bit here. Okay, so what are we doing here? Well, we're saying, let's say that we want to try and approximate the sine function over the interval -1 to 1, right? And so what I'm saying is, well, let's say we don't know what the sine function is. We have to approximate it. So we're going to approximate it by looking at the first few terms of the Taylor series expansion, right? So if you looked up the sine function, you would see that these are the first few terms of the Taylor series expansion. Now these guys are nice because they're polynomials, okay? And we're going to find as we go through the course that we love polynomials. But this isn't every term, right? There's actually an infinite number of terms in this Taylor series expansion. So by throwing away these terms, there is an error between sine superscript h and the analytic sine function. Are you okay so far?
Yeah, and I guess one question, what is that h superscript for? Is that the degree of how many Taylor series approximations we're doing?
Okay, good. Yeah, I'm glad you
Because
brought
at
that.
first I thought that was the sinh function, and I was
Right.
kind of confused.
Oh, that's good. I probably need to add a little line in the text. We use this h usually is always used to denote an approximation.
Okay.
Classically, it comes from taking the interval and chopping it up into a bunch of subintervals, all of which have length h. And so it's just kind of creeped into the literature as a way of denoting a function that's been approximated. Well, that's a great question. So here, what I'm asking you to do is, okay, why don't you go ahead and compute this on a piece of paper, right? You can actually just compute this integral exactly, right? And you'll get an error. And that error should be on the order of the terms that you left out, right? Then I want you to, instead of doing it analytically, why don't you use a quadrature rule to approximate this guy here, right? Which means you're going to just take like a 2-point Gauss quadrature, or, you know, I talk about a couple of the quadrature rules above. And what you'll see is that then this is like an approximation of an approximation, which is actually what happens in finite elements. You make an approximation because your subspace that you're looking for a solution in is not necessary, doesn't necessarily contain the true solution, but then you do numerical integration, which introduces another error. And so I'm just getting you to get your hands on this. It's a very simple little toy problem that you can kind of get your hands on that a little bit.
Okay, awesome. That helps a lot. And then kind of a follow-up question. In the Gauss-Legendre quadrature rules, in the remainder terms, there's that psi bar. Is that just the mean of the bounds that we're using?
Let me go up here and find that. It just means that it does come from the mean value theorem, but it just means that there is some location where this is the maximum kind of error in the approximation.
Okay, so it's for max error. Okay, that's good to know.
And so, you know, I just listed the first 3. These are called Gauss-Legendre quadrature. You can compute them for basically any number of points, and they keep getting more and more accurate as you go up in the number of points. So the point being that in finite elements, we integrate a lot of integrals, but we never do it analytically for the most part. It's always through an numerical integration procedure.
Okay, awesome. Thank you. That was really helpful.
Okay, any other questions on this?
I just had a quick question for those of us who are in industry. Greg told me the name of the person who was the TA. Can we ask that person questions as well?
Sure. Let me.
I should say, I at least think I know who the TA is.
I was just
Yeah.
there. We'll
Is
see.
it?
Well, it's
But
just
I wasn't 100% positive.
it's all my grad students. So let's see. How many? So I saw Caleb. Who else is here?
I'm here.
So Kyle is here and Caleb is here.
I'm also here.
Oh, there's Chris. All right, good.
I'm here too.
Oh, wow. All right. Get a full. So TAs, maybe Chris or Kyle, could you lead out and kind of just let people know kind of what your thinking is here in terms of how it, we've never done a class like this before, so we're learning here, but what's your initial thinking, Chris? And I think Chris, Kyle, and Caleb are going to be kind of doing some of the public work in terms of making themselves available to questions and helping you with your homework. I have a couple of other TAs on here that I may pull into doing some of the grading. But, Chris, Kyle, Caleb, any comments?
So I guess I was thinking basically I would be available for sure on Wednesdays 9 to 10, like it says there, for hours. And you can contact me to see if we can set up another appointment. I'll try and make that work, but for sure I will be available 9 to 10. Just shoot me an email. You have my email there beforehand, even for the scheduled times. I'm not going to be sitting there in a Zoom meeting just waiting for students to show up. But that's kind of my thoughts.
Can we send that list out to the industry folks via email or something if they don't already have that?
Yeah, can I give Caleb, Kyle, Chris, can one of you guys volunteer to do that?
Yeah, I can do that. And I would second what Kyle said. I think for us, it's a lot easier if it's just, if you need help, just send us an email so that we can, like Kyle said, we'll make ourselves available during that time. But if you want to be there, just send us an email so we can hop in that Zoom call. Otherwise, that's just a lot easier than sitting in a Zoom call for an hour, just waiting to see if anybody shows up. So I would
And I would add too that if there are simple questions that may only need an email and not in person, I'm at least happy to answer emails on any questions at any time.
I would also encourage people to use the forum that Dr. Scott set up. If people don't have that yet, and there's a whole topic in there for the grad course. And so, you know, oftentimes if one person has a question, multiple people have the question. And so if we ask it there, then
Yeah, here we go. You're talking about forum.coreforum.com.
Right. Yep. And you made a category for the IGA graduate course.
Yeah, right here. Okay, good. Yeah.
And so we can ask questions there, and then and then that helps other students see the, you know, get advice, but also it can help evolve the course as we move forward. So
Yeah, great. I like it. Okay. Other questions that I can help with, just doesn't have to be a homework question, anything we've gone over. Anything from anybody?
So
Yeah.
here's a question. The link on Learning Suite has, when you click on it, it takes you to a set of 3 questions, 3 exercises.
Oh, maybe I put in the wrong, let's see, let me look at the schedule here. So if you click on set 1.
It looked like set 1 and set 2 just went to the same place.
Okay,
So
that's a mistake. Yeah, that should be linked to, oh, yep, you're right. So the first set should be linking to the lecture notes that I've been going over this week.
Okay,
I'll fix that. Thank you, Rebecca, for bringing that up.
awesome.
Okay. Any of the engineering students want to voice any of their hidden concerns about all the math so that I can console you in any way? You guys doing okay?
Honestly, for me, so I did my undergrad in mechanical engineering, and a lot of just the symbols and just some of the terms we're using I had never heard of before. So I've had to kind of bear down a little bit this week, but that's kind of where I'm coming from.
Yeah, I
Yeah,
think
this is Eric Dodge, and I'm at the same place. Some of the terminology and some of the nomenclature and symbols that you're using are a little foreign. So maybe kind of talking about them a little bit as you're putting them down. Like, for example, there are times when you have a function and you're multiplying it by another function. Other times they're not functions, they're vectors. And I'm not quite sure whether they're functions or vectors based on what you're writing down. And so it makes things a little confusing.
okay, so let me see, is there somebody who can tell Eric how to solve that problem? So when you write mathematical literature, every time that you write down a function, what should you do? Here's an example. So how do we read this?
Function U that maps from domain omega to the reals.
Okay, so Eric, if you see a function, and I'm pretty pedantic about this, I don't usually introduce functions unless I introduce them rigorously. So if you go back to the function, it should tell you exactly what space the domain is, as well as the range of the function. And so that's commonly the way this is done correctly.
Yeah, so when I see a function, I typically define functions a little bit differently. That looks like probably a mathematician's way of defining a function. But
there's only one way to define a function, and that's it.
that's Michael Scott's opinion.
Well, I think it's the entire mathematical universe and science, and there is some very standard notations about the way you communicate these mathematical ideas.
Yeah.
And I'm trying to make them.
Dr. Scott, so like pause right there. So like in the example, I think what Eric's saying is that in your example, you say let f of x. And so I think Eric's reading that as function of x, right? Or, f, or is that z, whatever that is, x. And so is that your question, Eric, that you're expecting the notation to look like f of x?
Yeah, I just haven't seen that other notation that you've put at. So when you say the other notation, if you can go back to it, so that it is within the domain of, say that again so I can get that right.
So this is the canonical way, if I find an example, this is the canonical way that any function, any mapping is defined in any field.
So on the left, you have a function. If that's a function on the left, the parenthesis, some dot, comma, dot, parenthesis.
Mm-hmm.
So is that saying two functions are defined as a cross between two different vectors that are within the space of reals?
What this says is specifically this symbol, no matter what it is. It could be a carrot or an apple or whatever. Any symbol, this symbol is defined such that it takes an element of V in the first slot, another element of V in the second slot, and produces a real number. That's exactly how you read that notation.
And then right below it you have you use it, like where do you use that in an example, I guess?
Right
you
here.
use it with the symmetry definitions there, but
Is it?
The dots just mean those are input
Placeholders.
locations.
Yeah, so one of the things that I really hope the engineers get out of this is that it expands your vocabulary for being able to read the literature. This is the literature of finite elements. I mean, this is the way it's written. The notation that I'm using is very classical in this field. And so I'm hoping that over the course of the semester, you come back to it again and again. Most of the students at the end, they actually are most of the time they're like, yeah, now it's easy. Like after being exposed to it for a while, they get it, right? Yeah,
that's why we're here. We're here to learn. So teach us. I'm letting you know where I'm falling short.
Okay, good. Thank you.
Yeah, and Dr. Scott, going right along with what Eric was saying, is there some kind of reference for all of this nomenclature that we could refer to?
Well, I think that I'm defining it. I mean, nomenclature. Not that I'm aware of. I mean, I'm just
Okay.
kind of defining it as I go. Like this stuff, this first part here, all this notation is just classical calculus on the real line. This is standard notation. Then once we move into the spaces, this is pretty classical notation we're using for bilinear forms, inner products, norms.
So wait, what's the difference between your parentheses and your triangle brackets?
Well, again, you have to go back to the definition. So again, I define this symbol is defined to take these arguments into the reals, and it has these two properties. This symbol is this plus this additional third property. That's the way you read this.
So oftentimes you can find, if you just grab a math textbook, you'll oftentimes find like a list of notations in the very beginning of them, and that can be helpful. And sometimes you'll see like a book that has like a glossary of notations, but so you might just, if you've kept any of your math textbooks from your linear algebra courses, that might be a book to pull out and just look in the front and see if you have that. And that might be something that just has a concise listing for you.
Linear algebra and also real analysis talks about some of these abstract concepts, but a lot of familiar things with finite element.
Yep.
If the Hughes textbook might have a glossary too or something like that, but yeah, like Dr. Scott says, it is pretty classical, so you can just about pick up any FEA book and find a lot of this stuff too.
Another thing that I would say is most of this isn't even specific to FEA. I think if you have a good linear algebra book, you'll be able to find almost all of this in a good linear algebra book as well.
Yeah. So don't sweat it if you're feeling like, I mean, it'll be worth the effort. And I'm not vindictive about the math, but I do want to expose you to it and give you an opportunity to get familiar with it, because it will greatly expand the kind of work that you can do. Even if it's not finite elements, it'll expand, just generally speaking. These are the principles that underlie most of applied math.
And then Dr. Scott, if you just scroll up, you had two examples in boxes. So I thought these two might also kind of explain a little bit for Eric, or help explain what his question was, is that in these two examples, you have U and V in one instance are vectors, and in the next instance, they're functions, right?
Mm-hmm.
And so, but obviously they look the same. But
it's because it's an Rn. So vectors are in some Rn space.
Yep.
Here I say integrable functions. So I don't give you any more specifics other than the fact that you can integrate them.
Yep.
Yeah.
So just oftentimes.
So the other question I have is that you've defined that they're integral functions, U and V, and they're over a certain domain. And you're taking the integral of them, of U and V dx, but you never specified whether U and V were functions of x. So are we to assume whenever there's a function within an integral that it is differentiable by that variable? Or are there times when it will be and it won't be? And that, for like example, if you take a derivative of a function that's not a function of x, it'll just reduce down to 1.
Yeah, the dummy variable of integration is not actually very important. So you could pick any dummy variable of integration that you want to use here, but it won't change anything with respect to the nature of the inner product. So in some sense, it's cleaner, it's less confusing to some people to leave the dummy variable out. Yeah. Okay.
Less explicit, right?
Yeah. And there may be places, I mean, I'm writing these, like a week or two ahead of you guys of presenting them. So, if you find an area where I am not precise or I forget to add a definition, let me know and we'll improve them as we go.
I just went ahead and started a forum topic for mathematical notation. I'll put the
I mean, it's in the forum, but I just also put it in the chat. If you guys find anything, like, I'll probably YouTube some of this stuff. So like YouTube, Wiki, you know, whatever's accessible that helped you, post it up on that.
Yeah, great.
I'm searching for it.
Great, thank you. Okay, any other questions that I can answer before I move forward? Okay, well, let me bring to a close our first week of lectures by finishing up what I have been discussing with regards to, maybe I'll just annotate directly on here. Okay, so what can you see? Can you see the wiki page? Is that visible to everybody?
Yes, and you're at bases.
Okay, great. Okay, so yeah, we left off, we got through the energy spaces, and we gave an example of, and the basic takeaway conceptually or intuitively that I would say is important is that HK is really just CK. It's just a class of, it contains the class of continuous functions, and then you're throwing in additional functions that have the appropriate weak derivatives as well. And so the way to pin your intuition is really this close correspondence between the classical continuously differentiable spaces and Sobolev spaces. That's really the purpose for which they exist, is to kind of create a richer environment that has a lot of the structure of classic continuously differentiable functions, but contains a slightly more general idea of differentiability so that we can solve boundary value problems. And then when we talked about these embedding theorems, again, the intuition is we know that CK is contained in HK, but the question is, if you have HK, what CK space is it contained in? That's the question that it answers. And that, of course, becomes really very valuable when we go to discrete approximations, because we will be basically concerned with constructing piecewise polynomial approximations, which are a subset of CK spaces. And so that connection is helpful. Okay, so we use the term subspace to denote, so if I have V, here's my space V, and then I take a subspace, and again, I usually use this notation H, like we discussed earlier. And this, usually what this means at a high level is discrete, or in some sense finite, although a subspace doesn't really have to be discrete or finite. It can be infinite, but when we use it for finite elements, it almost always means discrete or finite. And so when we say subspace, we mean it contains function, DH contains functions that are in V, but another important property that has to be preserved is that it's still a linear space, which means if X and Y are in VH and alpha, beta are real numbers, then alpha X plus beta Y better be in VH as well. And so it has to preserve that linear structure in order for us to reason about it. Okay, bases. Now this for engineers is often a point of confusion, and it's hard because this is so important. It is really one of the foundational concepts in numerical methods in general, and really in the finite element method. So let's spend a little time here, and I'm not going to assume that you really know what a basis is. I've had enough experience that I realize that you've been exposed to this idea usually in the context of certain applications without kind of maybe understanding the general notion. So let me begin with a question, just at a high level. Can somebody kind of summarize for me, or maybe give me a good intuitive statement about what we mean by the basis of a space? Basis of a space.
Is it what defines like the most elementary like part? The most elementary definition of a space.
Oh, it's good, James. Yeah, you're going in the right direction. Yeah, so a basis is somehow you want to take a space that's filled with a whole bunch of things, and you're trying to distill out the key defining properties about everything in that space, right? So, you know, if I had a bucket full of apples, you might look through that bucket full of apples, and maybe there's a couple of different kinds of apples. There's Granny Smith's, there's, I don't know, what, Red Delicious, Fuji, whatever, right? Okay. What you could say is that, well, I don't need, no matter how many apples are in a basket, really all I need to know is that they're either a Granny Smith, a Red Delicious, or a Fuji apple. And so we would call this like the basis of that set of objects, right? It has distilled out all the defining characteristics of the space. And so what you want to do in mathematics, oftentimes in linear algebra and functional analysis, is this, you know, topic of what we're discussing, is you're dealing with spaces never in full generality. They always have some defining characteristics. And the way we make those characteristics precise is by defining a basis. Okay, so maybe it would be good to just discuss what would be like the first basis that you ever saw as an engineer in college. Can somebody maybe give me an example?
Polynomials.
Okay, great. So if you want to represent all polynomials, let's say all polynomials of degree less than or equal to 3. So that's a big set, right? So let's call that VH. How many functions are in VH? How many polynomials of degree 3 are there, right? There's A plus bx plus cx squared plus dx cubed. So any selection of coefficients is a distinct function that's in VH, right?
Yeah.
So it'd be infinite.
There's an infinite number of them. But what is the basis for the space? Somebody tell me, you guys tell me.
Are you looking for like a degree?
Well, I'm looking specifically for the precise, I want to write down exactly what the basis for all polynomials of degree less than or equal to 3 are.
Is it not just termite polynomial?
Is it like 1x squared and so on?
Yeah, 1x squared x cubed. Now notice, any object in VH, can't it be represented as any object? If I take U in VH and I have a basis, then I know that any U, no matter what it is, can be represented as a set of coefficients times, let's see, if we start at 0, that'll work, like 0 to n. Right? Any guy in there can be represented as a linear combination of coefficients times basis functions or basis vectors, depending on the space.
Question, you have x in here. I know that x can represent basically anything. It's like a dummy variable. But if you have multiple dimensions to this, it could still be a polynomial of degree less than or equal to 3, can't it? And still have multiple dimensions in it. Like, for example, you're in the x direction and the y direction, and you're defining a polynomial both in terms of x and y. And it's not a degree higher than 3, but you're defining a space that's.
Yeah, sure. We can have 1, x, y, x, y. Let's see, x squared y, x, y. So that's 2 dimensions, right? And then you just keep going up and up and up.
Right.
All the products, right? Of all the different polynomials and all the different, and that's still a basis for that multi-dimensional polynomial space. So returning to 1D though, notice that there's 4 base vectors or basis functions needed to represent any polynomial of degree less than or equal to 3, okay? And what's the requirement on these guys? Like, how do we know that we've got a basis? Like, how do we show that? Like, how can we be satisfied? Here we have enough experience with polynomials that like we can tell that we've got them all. But let's say you've never seen a polynomial before. How would you know that there isn't any others lurking out there that you didn't, you didn't account for? Like, how do you know if you have what's called a basis? What are the properties?
I mean, all things in the space can be defined by some combination.
So that's part of it, but couldn't we put 2x in here too, and then that would still be a true statement?
Oh, right. Linearly.
They're unique.
Exactly, that's the word I was looking for, the unique. And what we mean by that is they're linearly independent. Okay, and so like if you're, a lot of you have seen all these things, like maybe in the context of like, so here's x and here's y, and this, let's say this is R2, okay? Let's just write down quickly a basis for R2. What is a basis for R2?
1, 0, and 0, 1.
Okay. So any vector in here can be written as some coefficient times 1, 0 times another coefficient times 0, 1. And what do you know about these 2 vectors? How are they related to one another? Well, they're perpendicular. They're not linearly dependent, right? They're linearly independent because notice that these vectors don't share anything in common, right? There is no part of the vertical vector that's in the horizontal vector. So we know that what?
They're perpendicular.
Yeah, they're perpendicular, and we know they're linearly independent because this vector, the vertical vector, can't be represented in terms of the horizontal vector and vice versa, right? How about we pick 1, 2, 0, 1. So we have 0, 1, and then we have 1, 2. So it's 2 vectors. Are those guys linearly independent?
No.
Yes.
So how do we show that? They are in fact linearly independent, right? Because can you represent y in terms of the vector? Can you represent this vector here as a linear combination of some constant times this vector? You can't, right? Because this vector always has an x component to it. So no matter what number you chose to multiply no matter what number you pick, you're never going to be able to generate 0, 1. You agree with me? The only way that these would be linearly dependent is if this vector actually lied in this direction somewhere, right? These are all linearly dependent vectors. You see that? They're all in the same direction. They're just the only difference between them is the magnitude of the vector. So all these vectors on the diagonal are linearly dependent because they can all be written as multiples of one another. And the way that we say this in general is this equation right here. We say a set of functions or a set of basis vectors is said to be linearly independent if this holds, right? If we take a linear combination and set it equal to 0, then the only way that this happens is if CA is equal to 0 for all the A's, right? In other words, the only vector that satisfies this is the 0 vector. Okay, that is the defining characteristic of a basis. And what you'll find is that all of these vectors have that like these guys here from Rn, from R2, these guys, they're linearly independent, so you could do this. And I have you work a problem where it'll force you to kind of go through the thinking process here of how to do this, okay? Really what you do is you're gonna create, another way to look at this equation is to put a matrix. If we're to use these two vectors, you'd put 1, 0, 0, 1, A, B equal to 0, 0. And then what you want to show is that the only way that this holds is if this vector, the AB, is actually 0. That's equivalent to showing that this is invertible. So you just do row reduction on this guy until you get to a diagonal form, and then you know. But this is already in diagonal form, so you're done. Okay, so you know that that guy is linearly independent. Okay, so finite elements are all about basis functions. So when you create a mesh, why do you do that? Like why do you create a mesh? Most people are using finite elements. Why? And you spend time creating meshes. Like why do that? Like what's the point?
Because that's where we're going to solve our problem on, is on the mesh.
Okay, so we create a mesh, let's say, and then we know that the basic idea of a finite element method is we have to construct a space VH in which we're going to look for our approximate solution. So what is the relationship between mesh generation and this statement right here? We have a lot of finite element experts on the call.
Yeah, well, some of us couldn't unmute fast enough. You're creating your space to do the approximation. You're creating your approximation space.
Exactly. So what we're going to do is we're going to take this mesh and we're going to build little polynomials over each of the elements so that we get a piecewise polynomial space of functions, and the element structure tells us what VH is. So the whole purpose of generating a mesh and why it's important is because mesh generation is nothing more than saying I'm constructing VH, a linear subspace of where I want to look for my solutions. And that's why creating good meshes is so important, because this is everything, right? Like if you can't get a good VH, you're not going to get a good solution to your problem. And so this is the connection to the mathematics, right? Mesh generation is actually VH. So when I see a mesh, I don't see a mesh, I see VH. I don't know what that says about me, but that's what I see, VH, right? Okay, now, how many different bases are there? Like, even in R2, let's say we've got, again, R2, XY, R2. How many different sets of base vectors are there? Like, how many different bases can we construct for a given space?
Is it infinite? Because your base could be 2, 0, 0, 2, 3, 0, 0, 3.
It's infinite. There's an infinite variety of linearly independent combinations of two vectors that you can find in R2. So the question then becomes, what's a good basis? What's a good basis? This is a big deal for finite elements, right? What's a good basis? This leads to terms like conditioning, stability, efficiency, invertibility, and so on and so on and so on. They're nothing more than expressions of some characterization of what makes a good basis.
Mike, isn't it important that your basis can represent your solution space as well?
That's kind of what we mean by stability. Well, they're all kind of in invertibility. They're all kind of related to that. But in general, your discrete space will not be able to represent your solution exactly. But what you want is that it can create a good approximation. So I'm going to have you work a problem in the next homework set where I'm going to have you take the interval -1 to 1, and then I'm going to have you approximate the absolute value of x, which we showed was in H1, right?
Mm-hmm.
But it's not in C1. And then I'm going to have you approximate this with bigger and bigger and bigger sets of C infinity polynomials. So you'll be trying to approximate a rough function with infinitely smooth functions. It'll be interesting to see how well they do, right? Like what's a good basis here? Because C infinity functions, that seems like the worst possible choice to approximate this guy, doesn't it? And so you'll see that in practice, some of the trade-offs that we make. Okay, so for the finite element practitioners in the audience, in practice, what's the thought process that you go through when you're asking this question? Like, have I built a good basis?
First question I always ask is if it will represent the physics well. For instance, you know, your enrichment function at a crack front is different than what you use in most cases for solid mechanics.
Yeah, so if you know something about the physics, like maybe you know that there's a big spike in the displacement, or you have a wave front, or it's highly oscillatory, or it's fast physics versus slow physics, all that information that you have, you want to try and build that awareness into the basis functions. That's good, Curtis. What else?
Well, hopefully they're simple. Your basis is as simple as it can be.
Yeah, you want it to be simple, which is why FEA is popular, because it is simple. Simple tends to lead to ideas like robust and efficient, right? Because it's simple. We understand it well. We can implement it well, implement it efficiently. We get good run times.
Mike, how does this relate to calculating your Jacobian for mapping back to the reference configuration?
Oh, yeah. So, so what Curtis is asking is, oftentimes in finite elements, maybe we create a basis here, but then we compute the solution in some other wacky space, right? So there's a mapping here where we take a vector here and map it over here. And even though the basis has good properties here, the question is, when we map it into the actual space in which we solve for our solution, does it still have good spaces? And that depends on this. And I'll get back to that. I'll come back to that later. We'll talk about that. Right now, that just muddies the water, but it does have a huge impact. And in fact, that's why I assigned, or why I have this problem up here. See this change of variables? There's an implicit mapping in here. You see how mapping gets more complicated? And then I show you what happens to the integrand. And then this integrand, of course, is numerically integrated, but it's a much more complicated function, so that has an impact. Okay, so a couple of other things to wrap up. We characterize bases sometimes using terms like orthogonal, for example, if all the basis functions with respect to a given inner product have this property. Okay, so if A and B are the same index, then it's just the size of the vector squared or 0. We call those orthogonal, and sometimes this is a good trick to use for linear algebra. Makes solving system matrices easier. Another nice basis are called orthonormal. Those are orthogonal bases where every basis function is exactly size 1. Okay, so that's why in Rn we use these unit vectors, right? Because this is actually an orthonormal basis. Okay. For those of you who'll be working the problems, it'd be good, you're gonna have to use change of basis. So here's an extraordinarily generic, general expression for what change of basis means in terms of a given inner product in any Hilbert space. So you'll be using this a little bit, give you some practice for changing between different bases. That's a very important skill, and this is the entirety of it. And then the last concept, really just for your information, because it will be something that terminology that we use often, is the idea of an operator. So we'll often throw this word around, and an operator has a well-defined meaning. It's really just a mapping. So if I have two spaces V and W, an operator is nothing more than a mapping that takes entries in V into W. And then you can make further classifications and simplifications to this operator. Usually we always assume that these guys are linear, right? Which means if you take alpha x plus beta y and the operator eats that, it's going to spit out alpha mx plus beta my. So some examples of operators, a linear operator, the function f that takes x into c times x is a linear operator, right? So it's just scaling x by some value c. Every integral is a linear operator. They're called linear functionals usually. So any kind of an integral statement has this property up here where it's taking now, but now w is the real numbers, but it's linear. Any matrix between two finite dimensional spaces. So now it'll be R, let's see, R and to Rm. Any matrix is by default a linear operator. This is important. It's a nice property we exploit. And then there are some other properties that I'll come back to as we need them, like bounded operators, which by default then are continuous. Self-adjoint or symmetric operators. Those dominate structural mechanics. Positive definite also is a dominant feature of finite element problems in structural mechanics. So we'll come back to these definitions and show what they mean later in the context of some of our structural problems. And then another very important thing to know about an operator is you often want to know, like it says here, you want to know all of the elements in the domain of an operator where those guys are mapped to 0. Okay, so any structural analyst has dealt with the kernel of an operator. And you tell me where you do this all the time. Any of you who have ever run a quasi-static simulation have dealt with this.
You're removing the rigid body modes.
Rigid body modes is one way we talk about this. The rigid body modes, this is all linear functions, right? If you have the stiffness matrix, it will map all rigid body functions to 0. And so that means the kernel of the stiffness operator contains an infinite number of these objects, which means you can't invert the system, which is why you have to remove the kernel. And so we spend a lot of time understanding the kernel of operators, usually because we want to remove it so we can invert it. But sometimes in the context of splines, we'll actually leverage these to enforce smoothness conditions to build splines. So this is another picture for what a spline is too.
So Mike,
yeah,
the bell rang here, but I guess a comment I'll make then on that kernel is then the way that in practice we remove those rigid body modes again is by applying boundary conditions in the statics case, right?
Yep, that's exactly right. We remove the possibility of those modes being in the space, and so they go away. Okay, great. Well, have a great 3-day weekend. I'll see you guys on Wednesday. And please, BYU students, reach out to us. We want to help you, but we're going to leave it up to you to initiate those meetings. But let's get together and talk if you have any confusion. All right. Thanks, everybody.
Thank you.
Thank you.